Geiger Müller or GM counters are one of a class of gas-filled radiation detectors that operate by using the ionizing nature of alpha, beta and gamma radiation. Neutron-sensitive devices can also be produced, typically by introducing boron, which interacts with the neutrons to produce secondary ionizing particles that trigger the count response. The GM tube is a sealed metal cylinder containing a low-pressure inert gas such as argon or neon. A thin metal wire runs down the center of the tube, which is electrically insulated from the outer cylinder at the rear of the tube. The front of the tube is sealed with a radiation window that is specific to the typical radiation to be detected by the counter. For example, a thin mica window is used if the tube is to be sensitive to alpha particles and low-energy beta particles, both of which have low penetrating power. A thicker window, or a different material, such as glass or a thin sheet of metal, is used for high-energy beta particles, while for gamma rays the tube is often sealed without a window. In such tubes, the detection occurs when the high-energy photons liberate electrons from the tube's outer wall. The inner wire and the outer cylinder are maintained at a potential difference of about 1 kV, and in the absence of radiation, no current can flow through the inert gas between the central anode and the outer cathode. The connections are made via wires into a connecting housing that fits over the rear of the tube. An outer tube guard will typically screw onto this to protect the actual GM tube. This tube guard can be open at the end or be covered by an end cap energy filter to change the energy and particle sensitivity of the device, or, if a carefully calibrated design is used, allow for ambient dose measurements rather than ambient count measurements to be made. The wires connect the tube to the control electronics, which supply power, perform the counting operations, and provide other functions such as conversion from counts to dose, data logging, data averaging, and driving the display. The tube works on the principle of gas amplification. Incoming radiation ionizes some of the inert detector gas, resulting in a free electron and a positively charged ion. The electric field inside the tube attracts the charged ion to the outer cathode, while the electron is attracted towards the central anode. As the electron approaches the anode, the electric field it encounters grows in strength so that the accelerating force increases. Near the anode, the acceleration is such that the electron has enough energy to either excite the electrons in other atoms of the detector gas or to ionize them completely. Excited electrons quickly decay, releasing photons that can trigger ionization farther along the tube, while electrons freed by ionization can go on to cause further ionization, leading to an exponential growth. This is often referred to as the avalanche effect. The charge migration in the tube leads to a reduction in the potential of the anode and an increase in the potential of the cathode, either of which may be detected as a signal by the counter electronics. As the negative charge around the anode increases, the effective electric field is reduced, and eventually this reduction is such that further avalanches are not possible and the tube can no longer detect radiation. This state persists until sufficient electrons have recombined at the anode and positive gas ions recombined at the cathode, so that the field has recovered enough in strength to trigger another avalanche. This is the so-called dead time of the detector, the time after a detection that the counter is insensitive to further events, and its existence means that the detector count rate must be corrected to give the actual count rate. After the dead time, further detections are possible, but with reduced signal strength. The total time that elapses before the full strength signal is produced by a subsequent event is called the recovery time.